It's really great to be here. So I'm Lizzie, and I'm a data scientist. But my background is actually in astronomy and astrophysics. So that means I used to spend my time applying statistics to huge data sets of galaxies to try and learn about the universe. But now I still spend my time applying statistics to huge data sets, but now in online experimentation, it's to learn about humans and how humans behave differently in different situations. So since I've moved into the tech industry, I've been really lucky to work with some really great experimentation companies like Booking.com, who we heard about earlier from Lucas, and then Skyscanner, and I very recently moved to Split. And Split is a full-stack experimentation platform, but that's not what I'm going to talk about today. If you want to hear about experimentation at Split, you should come and find them on the lawn at the happy hour later. Today, I'm going to talk about experimentation at Skyscanner. So Skyscanner is a travel meta-search engine. So it's kind of like a European version of Kayak, if you know Kayak instead. And Skyscanner is actually a very mature experimentation company for its size. So Skyscanner has an in-house experimentation platform. It's run thousands of tests, and there'll be hundreds of tests running concurrently at any given time. And so part of my role when I was at Skyscanner was to support colleagues in designing, running, and analyzing their A/B tests. So I saw hundreds of tests coming through the platform, and I started to notice the same common mistakes being made over and over again. So we started to call these mistakes ghosts. So a statistical ghost is something which creeps into your analysis, and it makes you think that you've seen something. It makes you think that you've measured an impact, that you've had your test has really changed user behavior. But the sad reality is that there's no impact there at all, and you're just being fooled by the data. And this can actually be a really costly situation, because it can lead you to iterating on or maintaining a feature and spending your time and resources in doing that, because you think that you are having a good business benefit. But you're not actually having any impact at all, and your time could be so much better spent elsewhere. So today, I'm going to try and share some practical tips and guidelines so you can help you avoid that situation, and it can help you make sure that when you see a significant result, that you're really having a true impact. But first, okay, I'm going to try and do a brief statistics overview. So how many data scientists do we have in the audience? Yeah. Great, so you two people, you can go take a coffee break. But everybody else, so I hope you've already had your coffee, because I'm going to try my best to explain some experimentation statistics. And I think it's useful to have an example experiment in mind when we do this. So I picked a completely made up, but potentially real experiment based on Skyscanner. So imagine that you work with Skyscanner, and your goal is to increase conversion rate. So here, conversions can be a number of users who make a booking or book a flight. And based on design input, you think that changing the logo is going to help you increase that conversion rate. Well, if we formulate that into experimentation hypotheses, then that belief that changing the logo is going to change the people who make a booking is actually your alternative hypothesis. But when we run an A/B test, what we're really testing is the null hypothesis. And that's the idea that changing the logo is not going to have any impact at all on who makes a booking. And the reason why it's set up this way is because there's infinitely many alternative hypotheses that could exist. So changing the logo could cause a 5% change to conversion, a 10%, a minus 20%. There's just an infinite number of ways that you could change conversion. There's just that one exact situation where you have zero impact at all. So remember, when you're running an A/B test, what we're really doing is looking for evidence to reject that null hypothesis. So this is where a p-value comes in. So this up here is the technical definition of a p-value. I know it's a huge mouthful and probably not in any way intuitive. But what the p-value is really telling you is how unlikely it is that you would see the data that you saw if there were no true difference at all. So let's say we run the test and we change the Skyscanner logos, and then you get some X% change in conversion. What the p-value means is if we imagine that nobody cares at all about this change in logo, how unlikely is it that we would have got that X% change anyway? So really it's just telling you how much evidence do you have to reject that null hypothesis. And if you wanted to, I'm not sure why you would, but if you wanted to, you could actually work out the p-value just by running a whole bunch of AA tests, so not using any statistical tests at all. And that's because an AA test is something where we know that null hypothesis is true. So it's a case where we know there's no difference at all, and there's no difference in the performance of the treatments. So for example, if we were to send users in A to see the old logo and also users in B to see the old logo, there's no possible difference. So here I've simulated that situation of an AA test 100,000 times. So this is 100,000 simulated tests where there's no true difference, but we can see there's still a wide range of measured differences. And that's just because of the noise and random variations in the data. So you can see here that maybe one of those 100,000 tests had a measured difference of 8% difference in the conversion rate. So what this means is it's really unlikely for us to get an 8% difference in conversion rate if there's no true difference. So if we then run the test and we measure 8%, we're going to have a very low p-value, because getting this is very unlikely. So if I haven't lost you yet, I'm going to show you one more plot trying to show the same thing in a different way. So here, this is, again, those 100,000 simulated AA tests, but I plotted it cumulatively. So the way you can read this, for example, is that 60% of these AA tests had a measured difference of at least 1%. Because that's exactly what a p-value is telling us. So if we were then to run our real test, and we were to measure a 1% difference in conversion rate, what we would get is a p-value of 0.6. Because all it's telling us is the likelihood that we would have got that measured difference if we were running an AA test. So for these, a big change in conversion rate, like 7%, hardly any of those AA tests had that big a change. So then we would get a very, very low p-value if that's what we really measured. So remember, the p-value is telling us how much evidence do we have to reject the null. And this leads to a really interesting and very useful characteristic about p-values, and that is that when the null is true, when there's no difference between the treatments, then every p-value is just as likely as any other. So this is something which really surprises people. If nobody cares at all about us changing the Skyscanner logo, we are just as likely to get a p-value of 0.01 as we are to get a p-value of 0.99, because they're just uniformly distributed. So if we run an AA test, we're essentially taking a random number between 0 and 1. They're all just as likely as any other. And this is actually what allows us to use a very simple p-value threshold to decide if something is significant or not. Because of this uniform distribution, we already know what the chances are that something which has no impact is going to have a p-value which happens to fall below the threshold or above it. And this is how we set our false positive rate. Because we know if we use, for example, a 0.05 threshold, we have 5% chance of a p-value for a test which doesn't make any difference falling below that threshold. OK, so back to our example experiment. Let's say we do run it and we get this data. So we have 1,000 users seeing the old logo, 1,000 users seeing the new logo. We measure 50% conversion in A and 53% conversion in B. So we've measured a 3% uplift. Well, I put this data into a statistical test, and I got a p-value of 0.2. So remember, if you're paying attention before, what this means is that if nobody cares at all about the logo, we'd still have a 20% chance of measuring a 3% difference in the conversion rate anyway. Or if nobody cares about the logo and we ran 100 tests, 20 of them would show at least a 3% difference in conversion. So this is not a lot of evidence against that null. It's not a very unlikely result. So we put it into the test and we get 0.2, and it tells us it's not statistically significant. Well, this is a really important slide because people get this wrong quite a lot. Not statistically significant does not mean that your treatment had no impact. So if you see that result, you cannot immediately jump to the conclusion that your treatment had no impact at all. Because all it means is that you didn't have enough evidence to reject the null hypothesis. And when we don't reject the null, that is not the same as rejecting the alternative hypothesis. So be very careful that you don't see these results, not statistically significant, and then immediately assume you didn't have an impact. Because you could be missing something very beneficial, or you could be missing a very detrimental impact. OK, so that's the stats part mostly out of the way. And now we're going to get to the practical tips. So this is the 4 ghosts that I'm going to talk about. And remember, a ghost is a pitfall which leads you to see more false positives. It leads you to being misled by the data. And I picked these 4 because they're the 4 that I think I see most commonly. Most people make them more often. But they're also the most dangerous, so the ones that have the biggest impact on your false positive rate. So the first one is the ghost of multiple comparisons. And this one is a really tricky one, because of course, everybody wants to learn as much as they possibly can when they run their tests. But if you don't account for it, it can really make that false positive rate stack up and make it really hard to interpret valid results. So as we saw in our nice plot with p-values, we know exactly what the chances of getting a false positive are for one p-value. But this same chance applies to every single p-value. So for every comparison we make, we had that same chance of a false positive. So when we look at multiple things, naturally we have much more chance of a false positive. And this applies to looking at multiple metrics. It applies to looking at multiple treatments, maybe testing multiple variations, and also applies to looking at multiple segments. So for example, something that's very common is for people to run their test and then to look at how different user segments behaved. But these are all multiple comparisons, and they all bring their own chance of a false positive. So remember our example experiment. We looked at one logo, we looked at one metric, that's one comparison. We used a 0.05 threshold, so we had a 5% chance of a false positive. But let's say instead, the design team were not sure which color logo was better, and they had 8 ideas. So we test these 8 different versions of the new Skyscanner logo. Well, now, when we run this test, we then have 8 comparisons. So we use the same p-value threshold, and people would think that they're still getting a 5% false positive rate. But really, if you run this test, you have a 34% chance of a false positive. So that's a 1/3 chance that if nobody cares at all about the logo, you're going to waste your time making this big change because you've just got a false positive. And of course, it depends on how many comparisons you make. The more you make, the bigger this impact is. So for example, if we look at one logo, but we look at how users from 25 different countries react to it, that gives us a 70% false positive rate. So that means we're pretty much always going to see something as significantly impacted. So this 70% is huge, and people so often look at 25 different countries, and they're just asking to be fooled by this ghost. But as I said, this is a really tricky one. So this is a problem we had at Skyscanner. This is an example of our old version of our experimentation scorecard. So for every single experiment we ran through the platform at Skyscanner, we would compute these 12 top business level metrics. And we compute them because we need to know if we had some unintended impacts or how our changes impacted other verticals. But as I showed you on the plot before, computing 12 metrics for every experiment gave us a 45% false positive rate. So that means if everyone at Skyscanner was testing completely rubbish experiments, then almost half of them are going to look like they've had an impact anyway. So this is way too high, and it really harmed the trust in the platform. So the way that we tried to fix this was to introduce tiers to the metrics. So now we ask every experimenter to state upfront one key metric, and this will be the metric that their hypothesis is built upon, and hopefully the metric that they will conclude on. And we also allow them to choose a handful of secondary metrics, which are other metrics which are either particularly important to measure or which are more likely to be impacted. And then with these tiers, we're able to apply multiple comparison corrections. So I'm not going to go too much into detail here, but there are some links in the resources slide at the end if you want to learn more about them. So these are 2 most commonly used multiple comparison corrections. And at Skyscanner, we used a combination of both of these. But they both essentially work by taking into account how many comparisons you're making, and then adjusting your threshold so that you can maintain control of that false positive rate while still looking at many things. So they're a really useful way to get all this insight and look at many things, but while still keeping control of your error rate. And if you don't do that, if you look at all these many things, then it could very well be said that you are just peeing on the research. Okay, so I'm just going to wrap up on that ghost. So that ghost, the ghost of multiple comparisons, to avoid it, decide up front what your main metric is. If you're going to look at multiple things, then apply multiple comparison corrections. Or if you see something which is unexpected, something which is significant, but you didn't actually intend to target that metric in the first place, the safest thing to do is to rerun your experiment, but this time with that unexpected change as your main hypothesis. Right, the second ghost. Now this is the ghost of peaking. So peaking is a colloquial term for looking at an experiment whilst it's still running, or continuous monitoring. So hopefully, ideally, you would have decided before you started your experiment how long you should run it. But if you look at the data before then, especially if you take any actions based on that, then you are peaking. But it's tough because I know that people are very emotionally invested in their experiments, and they obviously are curious and excited to see what's happening, and they want to get to that result as quick as possible. But if you do this, then again, you can have a huge impact on your false positive rate. So as we saw in the statistics section, all the calculations for false positives and all of the statistics apply for one comparison at one predetermined conclusion point. And if you make anything other than this, you are always going to increase your false positive rate. So here's an example of an AA test, one of those 100,000 simulated ones I mentioned at the beginning. So this is a test which has no true impact, but I've shown the p-value as we would see it if we looked at it every single day. So every day, we take the data we've got so far, we compute a p-value, and I plotted it on here. And you can see that even though there is no true impact at all, the p-value just continuously fluctuates up and down anyway. And this is just noise. So the problem with this, a problem with peaking, is that if you keep looking at the p-values, then you have multiple chances of just happening on a result where the noise looks like a true impact. So you're just giving this ghost multiple chances to catch you out. And so if you were to see this, if you were to be running this experiment and looking at the results every day, then you might be tempted to stop the experiment after, say, day 4 or day 5, because the p-value is well below that threshold. So it must be significant, right? People think this all the time. But if you were to stop it then you wouldn't see that it eventually ends up well above the threshold because it's not significant at all. It's just an AA test, and there's no real impact there. So again, the more times you peak, the bigger the impact on your false positive rate. So if you were to stop an experiment as soon as it looked like it was significant, this is the real false positive rate that you would get if you expected a 5% false positive rate. So for example, let's say you run an experiment for 3 weeks, 21 days, and you look at it every single day, and you stop it as soon as it becomes significant. If you use a threshold of 0.05, you probably expect you're getting a 5% false positive rate, but what you're really getting is 25% false positive rate. So that's 5 times as much chance for false positive. So this really does have a huge impact. But statistical rigor aside, I do realize there are many good business reasons to peak, so the reasons to look at the data. So you want to check that it's running correctly, that it's getting data in, that there's no bugs. If there is a disastrous impact, you probably want to stop that experiment. So you can look at the data, but you need to make sure that you look at it safely. And the easiest way to peak safely is just not to act on what you see unless you really have to. So don't be tempted to stop that experiment early because it looks like it's significant. Or you can use different statistical frameworks that actually allow you to stop an experiment at any time. And these are called sequential testing frameworks. And again, there's links at the end if you want to read about going down that route. So to avoid the ghost of peaking, just remember it's fine to look at the data, but just don't act on what you see. Don't be tempted to stop an experiment early because you think it's significant. So the third ghost then, I've called bad metric, wrong test. And this one is all about measuring the right thing in the right way. And it's a subtle one because people often overlook how important this is. So these are the 4 things that I think are most important for a good metric. I think a good metric is meaningful, it's interpretable, it's sensitive, and it's fit for the statistical test you will apply to it. So I'm just going to go through them one by one. Firstly, a good metric is meaningful. So by meaningful, I mean the metric is really capturing what you are intending to change, and it's really capturing something that's bringing actual real business value. Here's an example of a not very meaningful metric, and it's a story some of you might have heard of already. It's about a Chinese shoe company who released an Instagram advert with a fake hair over their image. So their idea was that people would try and swipe away this hair on their phone, and they would swipe it, and they would accidentally click the image. Yeah. So I'm going to guess that this experiment actually was optimizing for click-through rates, right, or clicks on the image. And I'm pretty sure that it did really great on that metric. But it actually ended in them being banned from Instagram advertisement. And I really doubt that it brought any meaningful business impact. So this is an example of not a very meaningful metric and of essentially gaming the system. And then a good metric is interpretable. So what I mean by interpretable is that when the metric moves, it's very easy for you to tell how that changed user behavior and also whether that was a good or a bad thing. And this is an example of a metric which caused us quite a bit of trouble at Skyscanner. So it's the fraction of sessions that convert, or the number of conversions over number of converting sessions over the number of unique sessions. And people often wanted this because it's kind of historically used for business reporting. So people want to match the business KPIs. But it's not a very interpretable experimentation metric. And the reason for that is both the numerator and the denominator of this fraction can change. So you can change the number of sessions, or you can change the number of conversions. And both of those can be a good thing. And if this metric changes, you don't automatically know which one of those changes or whether it was a good or a bad thing. So this is not a very interpretable experimentation metric. And then a good metric is sensitive. So sensitive means that your metric is able to measure and detect those smaller changes faster. But this is really quite a hard one to get in your metric because some metrics are just not inherently sensitive, for example, revenue. but obviously they're very important to measure anyway. So it's not always easy to get a sensitive metric, but there are ways that you can improve the sensitivity of your metric if you really need to. For example, variance reduction techniques, or you can use some outlier removal in the data. And then this last one is a really important one. So the metric that you use must be fit for the test that you're applying to it. So common, most standard statistical tests, like a t-test or a chi-squared test, assume these two things. So they assume that the observations are independent, and they assume that the error or the noise in the data is normally distributed. And that second one is usually fine if you have a decent enough sample size, but the first one can often catch people out. For example, a common one is when people allocate users into A or B, but then they try and look at per session metrics or per click metrics. Because the problem is that if you're allocating users, then a user's second session probably depends on their first session. And these observations, they're not independent. So you can't safely put these into one of these standard tests. There are techniques you can use to look at these kind of metrics. For example, the delta method or bootstrapping. And again, there's links in the resources slide. But don't get caught out by this, because it's such a common thing that people want to look at, but they don't fit the assumptions of the test. So for example, in our Skyscanner logo example, because Skyscanner allocates on users, then looking at something like conversions per user or fraction of users who convert is fine. But if you look at conversions per session or conversions per search, this is not okay, because those observations are not independent. And if you try to use this kind of metric in a standard test, it will give you a much higher false positive rate. So just to recap that one, a good metric is meaningful, a good metric is interpretable, it's sensitive, and it satisfies all the assumptions of the test that you're going to apply to it. Right, and then the last ghost. So this is something that drives me pretty crazy, because I hear it all the time. And this ghost is, I guess, the ghost of temptation. It's something that people, people often want to believe what they're hoping for, and you want to conclude, and you want to see what you were hoping for. But that's not how statistics works. So remember we saw this plot before, and we said that every p-value is just as likely as any other when there's no true impact. Well, that means that a low p-value is not necessarily indicative of an impact, or it's not, when we use our threshold, we do that so that we can fix our false positive rate. And if you try and think that something that's near the threshold is actually a real impact, then you're increasing that false positive rate and you're adding bias. So there is no such thing as almost significant. Yeah, I think the two data scientists in the room just clapped there. There's really no such thing at all. There's no trending to significance. There's no kind of significant, barely significant. There's just no such thing as almost significant. It either is or it isn't. So if you want to avoid this ghost, then just follow these two simple guidelines. If that p-value is below that preset threshold, then that's great. You've got evidence to reject that null hypothesis. You can say that you've really measured something. But if the p-value is above the threshold, even if it's very slightly above, the only thing that you can safely do is to remain uncertain and to act as if that data is noise. It's either significant or it isn't. Okay, so those are the four ghosts. I'm just going to quickly recap them. So the first one we met was the ghost of multiple comparisons. So to avoid this ghost, decide up front what your main metric is. If you're going to look at more things, apply multiple comparison corrections. Or if you see something unexpected in the data, then rerun the test. Then we saw the ghost of peaking. If you look at the data while the experiment is still running, don't act. So don't be tempted to stop that experiment early because it looks significant. A good metric is meaningful, it's interpretable, it's sensitive, and it must satisfy all the assumptions of the test that you're applying to it. And then finally, we just met the ghost of almost significance. There is no such thing as almost significant. Thank you.
Thank you very much, Lizzie. That was fantastic. Thanks. And we have a lot of questions for you. Some of them will probably take you quite a long time to answer, but let's see what we got here. If multiple variations increase risk of false positive, why should we ever do multivariate testing?
Yeah, well, if you have enough traffic, then you're able to apply these multiple comparison corrections and still keep that false positive rate down. So the reason why you might want to do this is because you're able to test multiple things at the same time, especially for multiple variate testing. You're able to see which elements of the change have the best combination, have the best impact. So these are useful techniques, but they really require a huge amount of traffic. So I think in most cases, you're not going to have enough traffic to do this properly. And if you're doing this without applying that correction, then you probably just shouldn't do that, yeah.
If a test seems to be tanking early, possibly affecting CPL or metrics that are important, and marketing is freaking out, at what point do you pull the plug?
Yeah, so I'd say this is not a question for a data scientist. This is much a strategic question. So the point to note is that if you stop that experiment early, then you can't learn from it. You can't conclude it. You're basically voiding that experiment. So it's up to you. If you've decided that this experiment is too costly to continue, then you can stop it, but just don't try and say that you learned from it.
This one is kind of off topic, but it had to do with you introducing your background. Should we do it or not?
Well, I can't prove they don't exist.
And that's the data scientist speaking. Yes. How do you manage scenarios where you see a significant result in an experiment, but those results are not shown post-launch in the overall business metrics?
So it happens sometimes, for sure. So we know we have a 5% false positive rate. So it depends on how often you think you have a real impact. But if you only have, say, 10% of your results showing a significant impact, then it's not unreasonable that a fair chunk of those are in that false positive range. I think it's hard to be sure, though, that post-experiment you're not seeing that impact because we're no longer running an experiment. So maybe you don't see it, but maybe if you hadn't put that feature or that change out, the metrics would have gone down. So it's very hard to be confident of what change is actually happening if you're not running an experiment.
Let's do one more. Have you researched the calculation CRO tools used for confidence and margin of error? And, and what were your findings? Are those tools known for more false positives?
Ooh. Well, so I think it depends on how you interpret the output of those tools. So a lot of these tools will leave a lot of flexibility to the user. So it's more up to you into how you interpret those results. So people don't often say, go for it, launch that feature into production, but they'll tell you the data and they'll leave it up to you to interpret it in the right way. And if you are aware of these ghosts, hopefully you can now do that.
Awesome. Thanks again.
Thank you.